Sushruta for NEET is now available on the Google Play Store. Try it out for free.
All right, so here we are. I hope everybody is ready for another this follow-on chapter with current electricity. So today we will try to go through some of the chapters for current electricity. I may not get through everything, but I'm hoping to get through as much as I can. But before I get started with my material, I'm going to first introduce to you our Independence Day special. Between now and the 15th or maybe the 17th of August, all students who register for Sushruta for NEET or Ramanujan for JEE, you're all in for a special treat because we are reducing prices, 30% reduction in prices for the 6-month plan, $39.95, for the 1-year plan, $59.95. So hurry up, these offers will not last. You miss the deadline, it will go back to its normal prices. You are welcome to contact Kushbu, or just go to play.google.com, look for com.jnanamarga.sushruta, and you will get the Sushruta, or com.jnanamarga.ramanujan. Either will get you to the app, and then you register, and then you complete your payment, and then you will be all set to go for the $59.95 payment plan. You know, or the $39.95 payment plan if you're looking for a 6-month price. Remember that many institutes charge in the lakhs now, and some of them charge several thousand for a 1-month program. This is a 1-year program for 6,000 rupees. You know, you will get tremendous benefit over the period, and you will have a very good chance to succeed here. So today we will look quickly at power, and then we will look at this resistance combination, and how to look at solving resistance combinations, some examples, and then power dissipation. Then we will switch gears and we will go to Kirchhoff's current and loop law or voltage law. Okay, so electromotive force is EMF is not is really about the voltage, and it's not about power. You know, it's not a power supply. Rather, it is a pickup low energy or potential. What it does is you get a potential drop along the circuit, right? So now the potential difference across the ends of any resistor, right, is you have at the on one side of the resistor you have VA, and then on the other side of the resistor you have VB, and what you have is the potential difference across the resistor, which is called VAB. Remember, VB minus VA minus VB is the potential drop, and when the potential drops, you can call the potential difference VAB, right? And therefore VAB equals IR, right? So VB equals VA equals VB plus IR. So A is at a higher potential, B is at a lower potential, and the drop is equal to IR. Okay? So VAB equals IR, and now when we look at the power, it is I squared R, V times I. The potential drop is IR. IR times is the potential drop times the current is the power. V times I is the power. So potential drop across the resistor depends upon the direction of the current, right? So if the current is flowing from A to B, right? So then we say that VA is higher and VB is lower. Okay, so that is the normal convention. Power is V times I or I square R, because V is itself equal to I times R. So therefore you end up with I square R or V square by R, or basically it's V times I. In transmission lines, power is dissipated due to the resistance of various wires. So resistance causes the current to get converted to other forms of energy. In the case of the electric lamp, it becomes two forms of energy. One is light and the other is heat, right? So the power is I squared RC across a resistance cable, and therefore that's how the section AC here absorbs 64 watts of power, right? How do you know that, right? So we know the current flowing through it, and then if you know the resistance, then you can get the voltage, the wattage, right? So VAC equals 64 divided by I, right? And I is 1.6, therefore the VAC is 40, right? Now, so VAB is 1.6, right? Therefore, the 1.6 is the current times the resistance 20, therefore VAB is 32. Okay, so now what we're going to look at is a series combination of resistance. Two or more resistors are in series, we know it as a series combination. In series combination, the current is the same and the voltage is the sum, and therefore when we look at the combined resistance of a series combination, we just add the individual elements. So R1 plus R2 will give you plus R3 dot 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 if you have n resistances in series, that you represented each resistance by that sign, right? So 1, 2, 3 and so on. So you just R1 plus R2 plus R3 is the effective resistance. Series combination, sigma REQ equals sigma RI, right? And the potential drop just keeps adding up, right? Now, when the resistance is in parallel, right, what happens? There is one resistance, then there is another resistance in parallel, right? So the voltage across both resistances are the same, right? So V divided by REQ equals V divided by R1 plus V divided by R2 plus V divided by R3. Therefore, 1 by REQ equals 1 by R1 plus 1 by R2 plus 1 by R3. The current is not the same, right? In the series, the current was the same. In parallel, the voltage is the same. Okay, so remember, that's how you end up with 1 by REQ equals 1 by R1 plus 1 by R2, and so on, right? And therefore, the current branches out. The current coming in I is equal to I1 plus I2. When a potential difference is applied across the combination, the same PD appears across each branch. Okay, so what is the equal resistance? 1 by R1 plus 1 by R2 equals 1 by REQ, right? So now if you had a example of a series and two parallels, right? So what is the effective combination of all three together? First, let's evaluate the effective combination of these two. The effective combination of these two is R2, R3 divided by R2 plus R3. That is evaluate how do you say that that is the value? 1 by REQ equals 1 by R2 plus 1 by R3, and if you simplify that and cross multiply, you will find that you take the LCM will be R2 R3, numerator will become R2 plus R3, therefore REQ equals R2 R3 divided by R2 plus R3, right, for this combination alone, right? BC, right? So the voltage across BC will be I times, right, R where I is the total current flowing through here, right? So that I times Req will equal the voltage across BC. Okay, and so that's how you can solve, right? The other way is to say I equals I1 plus I2, and then you write, you introduce a second variable VBC equals equals I1 times R2 is also equal to I2 times R3, right? And therefore, you can write the ratio between I1 and I2, right? I1 by I2 will equal R3 by R2, right? And so once you have that equation, you can then use that equation, two equations and two unknowns. Okay. So, but the simple way to do that is to write the equivalent resistance R2 R3 divided by R2 plus R3. So I times R2 R3 divided by R2 plus R3 will give you the resistance. Okay. So now what is the voltage between VA and VC, right? There is a voltage drop here, and then there is a voltage drop here. You replace these two with an REQ, with a single resistance REQ, right? So R1 plus REQ will be the effective resistance between A and C. And if you say I is the current, VAC equals R1 plus REQ times I. So VAC divided by R1 plus REQ will equal I. Okay, so that's how these examples are solved. You get the equivalent resistance of the whole thing, and then you multiply that by the current. It will equal the voltage across the whole thing. So that's one way to solve it. The other way is to use these separate equations and break it up and solve. So now I'll discuss this problem. This is a simple example, right? So you have two resistances in parallel, 20 and 3, and you have a third resistance in series with these two, right? So what is the equivalent resistance of 2 and 3? The equivalent resistance of 2 and 3 is 2 times 3 divided by 2 plus 3. 2 times 3 is 6, 2 plus 3 is 5. Therefore, the equivalent resistance is 6 by 5, right? So this is this is currently 2, right? So the effective resistance between this point and this point is 2 plus 6 by 5. It is 16 by 5, right? So what is the voltage across it? 8 volts, right? The effective resistance is 16 by 5. So 8 divided by 16 by 5 will give you the current, right? And he evaluates that right here. 8 divided by 16 by 5 equals the current. That is 8 divided by 60 by 5 is 5 by 2, right? 5 by 2, right? And so now, once you evaluated the current, right? So what is the voltage drop between this point and this point? 8 volts, right? So what is the voltage drop between this point and this point? You know the current, it is 2.5. It's 2.5 times 2, right? What is the voltage drop between this point and this point, right? So this is 5. So that is, what remains, right? It is 6 by 5 times 2.5. Okay. Now, what is the current through this one, right? To get the current through R2, you have the total voltage between this point and this point, right? That is what? 6 by 5 times 2.5, which is 3, right? So the voltage between the voltage across R1 we said is 2 times 2.5, right? This is 5. The voltage across REQ is 3, right? So 5 plus 3 is 8, as you notice, right? So now, if the voltage between this point and this point is 3, and this resistance is 2 ohms, what is the current? V divided by I, right? the voltage is 3, the current is 2, therefore the resistance is 2, so therefore the current is 3 divided by 2, 1.5. What is the current through this branch? Two ways to evaluate it. Incoming current is 2.5. Current through this 1.5. So the remaining 1.5 has to go through the other branch. Or you look at the voltage drop between these 2 points. It is 3. It is same as the voltage drop across these 2 points. It is 3, right? So the current through this is 3 divided by 3, just as the current through this was 3 divided by 2. Notice that the voltage between this point and this point is specific, is a function of this point and this point, right? So there is a voltage at a point, there is current through branches. Okay, so remember that you have a voltage at a particular point, voltage across 2 points, right? A potential drop across 2 points, or a voltage drop across 2 points, right? And you have current across branches. Okay, so I coming in equals I1 plus I2, right? So these are actually the laws that you will use, okay, when you learn Kirchhoff's laws. So now here is an example. Initially the switch, this is a 21 volt battery. There is 4 ohms, 8 ohms, 12 ohms, 8 ohms. Okay. Now there is a switch connecting these two. Initially this switch is open. Okay. When this switch is open, what is the equivalent resistance? There is 12 here, 12 plus 8, 20 here. Okay. So now when the switch is open, this is an open, right? So 4 plus 8 is 12, 12 plus 8 is 20. So 12 and 20 in parallel. What is 12 and 20 in parallel? 20 times 12 divided by 32, right? 20 times 12 divided by 32 is what? That is 7.5, right? So 7.5 is the resistance. The current is the total current through this branch will be 21 divided by 7.5. Okay, so that will be the current through this branch. Okay, what is the current through this branch? It will be 21 divided by 12. What is the current through this branch? 21 divided by 20. Okay, so the sum of those two currents will equal the total current here. Okay, so understand the logic and keep careful track of it, right? And then we will, when we discuss Kirchhoff's laws, it will become very, very clear what's going on. Now, when you turn on the switch, right, these 2 points are connected. Okay, so then you will end up with resistance 1, resistance 3, the R1 and R3 will be parallel. Then that pair will be in series with R2 and R4, which themselves will be in parallel. Okay, so what is R1 and R3 in parallel? 12 times 4 divided by 16, divided by 12 plus 4, which is 3. What is 8 and 8 in parallel? 8 and 8 in parallel is just 8 by 2. Okay, 4. Okay, so you have 16, and then you have 8 times 8 divided by 16, which is 4, right? So so you have when you have 12 and 4 in parallel, you have 3, right? So 3 and 4, so the effective resistance will become 7 when you connect the switch on to on, right? So the effective resistance will become 7. What is the effective current? It will become 3 amperes. 21 divided by 7, right? So 3 amperes, and then you can see how each of the branches will break up, right? And how the voltages will break down, right? So if if the total current is 3 amperes, right? Now you can tell for R2 and R4 it will become 1.5 and 1.5 because it's symmetric. For R1 and R3 How do you find out? Right? So for R1 and R3, right, you must, if you assume that, the voltage at this point is fixed, right? Yeah, so, and it's connected, right? So you introduce that voltage. So V, uh, V divided by 4, let's say V is the voltage across these points. V divided by 4, right, equals V divided by 12. Okay. No, V divided by 4 plus V divided by 12 equals 3. Okay. So what is V, right? So what is the voltage at that point, right? You will get an answer, right? So you have only one variable, which is V, right? So once you get the V, that V divided by 4 will give you the current through R1, and V divided by 12 will give you the current through R3. So if you asked me, I would quickly look to say that it will be inversely proportional, right? So if this is 3, it will go so that this branch will have 1/3 the current as this branch. This branch is going to have 3 times the current. So 3 times versus 1 time. So if you had 3 ohm or 3 amps, it will become 2.25 and 0.75. So in the ratio 3:1. Okay, and these two are equal, so it will be half and half. Okay, so roughly these are very linear relationships, and they follow ratio proportion. Okay, so that's how you do simple circuits where you find equivalent circuits. So now when you have to do power dissipation in series and parallel, if you wanted to find the power of each of these resistance, you get the I, you get the I, get the I, you get the I. We found the total I as 3. We found this one as 2.25. We found that one as 0.75. If you wanted the power dissipated in this resistor, you have I square R. Power dissipated in this resistor, you have I square R. If you got the V, then you can do V square by R. So in this case, right, we said that the effective resistance, right, was 7, right? The effective resistance 7, the current is 3. Therefore, the total power is I square R. So 7, so 3 square is 9 times 7. Okay, so that will be the power drawn by the whole circuit. And each of the resistors will get one part of the power. The sum of all the powers will equal this calculation that we did, which is 63. 9 times 7. 3 times 3 times 7. Okay. So that's how you solve these the power, right? And so the power dissipation is more like in parallel than series. That's why we prefer series of LEDs in festivals rather than parallel. Okay, so so that's the thing. Only thing, parallel, it will hopefully burn brighter. Right? If it burns brighter, then it will consume more power. There is no free lunch. Okay, so so that's how you solve these problems. The power is V square by R or I square R. So you solve the circuit and then you find the equivalent power. So now, so in this question, we looked at the power. So now when we, here is another example. I am not going to go into this example because we don't have all the details here. Okay. So, but basically there is the parallel combination R1 plus R2, right? And the voltage across the total is 240. So the current through each of them is R1 seems to be 960, R2 is 640. So the current through each of them is given by I1 equals 240 by 960 and 240 by 640. So you have 1 by 4 amps, 3 by 8 amps, then you do I square R across each of these. Okay. So that is the how you solve these problems. Okay. These are much simpler problems than you would otherwise find. Okay. So now I'm going to move on to the to the next set of details that we will look at. Okay, and the next set of details is when we look at cells in parallel and series. Okay, and then we try to look at also what happens. We will introduce the beginning of Kirchhoff's laws as well. Okay, so now series combination of cells. So basically, every cell also has an internal resistance, as you know. So when you put cells in series, the voltages will be additive. When two or more cells are added in series, is known as series combination of cells. So what happens, right? So the voltage between C and B is E2, between B and A is E1, right? So the effective voltage in an open circuit will be E1 plus E2 between these 2 points when there is no current. When there is a current, the voltages across the resistors, the internal resistors, will have to be added. So VC minus IR2 plus E2 minus IR1 plus E1 equals VA. Okay, so here there is a current going this way of value I, right? So if you say that there is a current going this way, right? So you say minus IR2 plus E2, okay, minus IR1 plus E1 equals the VAC. Okay, A is that much higher than C when you evaluate it. You replace it with this, you will end up with this. Okay, so if you needed to replace these two, right, you write when two cells are in series, the effective voltage is E1 plus E2 in series with R1 plus R2. So this is the effective E1 plus E2. The effective R is R1 plus R2. So EQ is E1 plus E2. REQ is R1 plus R2. Very simple, right? But let's not forget to note it. In series combination, we know that the current remains the same, but potential changes, right? And to derive that equation, remember that when you go from the small line to the big line, and you go, let's say the small line is here and the big line is here, and the current is going this way, right? So or don't forget about that. Just when you have the small line, the big line, right? When you go from the small line to the big line, you have a plus, and you go this way, right? If you go this way, it's a minus. Okay, so if you start here and go this way, it will be minus. Okay, so and in any resistance, if let's say the current is going this way, this is a minus. This is a resistance, current is going this way, it's a minus. Current is going this way, the resistance is here, it will be a minus. I times R leads to a potential drop. Okay, so that's how you evaluate. Go one loop around any circuit, you should get 0 because you've come back to where you started. Okay, so that there's a law for it, and I will discuss the law just now. Okay, the equivalent internal resistance is equal to the sum of the resistances. Now, when you have two voltages in parallel, it's a little bit trickier. What is the effective resistance, right? The effective resistance of this circuit is this this one. It is 1 by R1 plus 1 by R2 is the effective REQ. Okay. Okay. And the EEQ, so this is the effective REQ, right? The EEQ is this one, a much more complicated term. Okay. So how do you arrive at this term, right? So you calculate the whole, you write the I, you write the I coming in equals I going out, right? Whatever current is coming in is going to go out, right? And so that is I1 plus I2, and that is equal to E1 minus V by R1 plus E2 minus V by R2, right? And therefore, you write this as I times this plus whatever else, right? That whatever else is this complicated formula. E1 R2 plus E2 R1 divided by R1 plus R2. Okay, so that is the EEQ. Okay, that is the equivalent of in a parallel combination of cells. I would memorize this one. You should definitely know this one, but this one I would memorize, make it, because it's not so easy to quickly derive. Okay, so E1 R2 plus E2 R1 divided by R1 plus R2. Okay, so it's worth learning. Okay, so that is the EEQ of cells in parallel. Okay, so having explained that, right, in parallel combination, the equivalent EMF is equal to the summation EMF of cells divided by the internal resistance of the of that cell. Okay, what do they mean by that? That is, they mean this formula. What is the summation equivalence? E1 R1 plus E2 R2 divided by R1 plus R2. Okay, so E1 R2 plus E2 R1. So note the switch, right? E1 R2 and divided by the internal resistance, right? And we have the summation. Okay, so the equivalent resistance is just merely the resistance in parallel R1 R2 divided by R1 plus R2. So just replace that, then you solve. Okay, so that's a very simple way of solving. Okay, so so EEQ divided by REQ equals E1 by R1 plus E2 by R2. Okay, that will give you the effective current as well. Okay, so if you wanted to find the currents, separate currents, I goes I1 plus I2, right? I equals I1 plus I2. You can find that using this formula. Okay, so you typically, if you have parallel cells, right, you build this EEQ, make it one cell, EEQ and REQ, make it one cell, and then you solve the whole circuit, and then you use the fact that you can then divide it into R1, E1 by R1 and E2 by R2. Okay, so that's a very straightforward way. So here's this problem here. He has got three cells in parallel. So you have I coming in equals E1 minus I1 plus I1 plus I2 plus I3 times 1 equals 0. Okay, so he's got three equations and three unknowns, right? So I1 plus I2 plus I3, the current across going through this one. So 1 times I1 plus I2 plus I3 is the voltage drop across this, right? So E1 minus I1 E1, right, minus or this one, right? Sorry, this one. E1, right, minus I1 times 1. He's written it the other way, right? E1, right, minus I1 times 1 minus I1 plus I2 plus I3 times 1 equals 0. Okay, so now using this, he ends up with one equation, okay, which involves 2 times I1 plus I2 plus I3. That produces his first equation. His I1 equals E1 minus E2, okay, and I3 equals minus 1, and I2 equals 2, okay. So he ends up with a very complicated equation because of that, okay. So one way, what I would do in solving a problem like this is you replace these two, right? Replace these two with by applying this formula and find E, EQ and REQ. For this one, EEQ plus R-EQ will be R1, the REQ will be R1, R1 R2 divided by R1 plus R2, and EEQ will be 2 times 1 plus 3 times this value divided by R1 plus R2, right? So now you've got the equivalent of these two. Then I will do that one more time with the EEQ and REQ with this one. Okay, I'll do it second time and find the resultant EQ, and then I will solve. Okay, then I will have an internal equivalent resistance and 1 ohm along with it, right? So that will produce you the effective resistance. Okay, so that's what you should do in solving these problems. So here you have the exact same thing. So how do you do? What is the REQ here? 0.15 times 0.15 divided by 0.15 plus 0.15, right? So that is nearly 0.15 by 2. Okay, so you have 0.075. Okay, now what is the effective EQ? It is 1.2 times 0.15 plus 1.2 times 0.15 divided by 0.3. So 2 times 1.2 divided by 0.15. So it is still 1.2. Okay. Now, so it is the equal EEQ is 1.2, the REQ is 0.075, and therefore you end up with so 0.075 plus 2, 2.075, 1.2 divided by 2.075 will give you the current. Okay. So now, having explained all this, you already know at some level what Kirchhoff's laws are. Okay. Now, what Kirchhoff's laws say is that in any circuit, regardless of how complicated or how easy it is, at any junction, right, the current coming in is equal to the current going out. So I1 plus I2 will equal I, the effective current going out. I1 plus I2 equals I. Okay, so and you can use any convention. You can use current like this or current like this. You must just follow that convention. If you say current coming in is on the left hand side, I put all the currents coming in. The right hand side, I put all the currents going out. Okay. Otherwise, you put all the currents where you use the same convention and you set that to 0. Okay. So I1 plus I2 minus I equals 0. I put incoming is plus, outgoing is negative. So I1 plus I2 minus I equals 0. Right? So all the currents coming into to a junction is 0. Just follow the plus and minus convention. Otherwise, you write it as I1 plus I2 equals I. All the current coming in is equal to all the current going out. Okay. So that is called Kirchhoff's junction law. So at any junction and every junction, the current coming in is equal to the current going out. Okay. So then there is the loop law. The loop law says that in any closed network is called a loop. Any closed network. Okay. So, and if you go once round that any network, you will end up with 0. So the voltages drop back, right? So when you go once around, you should end up V minus IR1 minus IR2 minus IR3 dot equals 0. So you go once fully around, you will end up with 0. The temptation will be to sometimes not do justice to the number of equations and unknowns. The circuit solves itself, but the number of equations and the number of unknowns are very typically exactly the same, right? You don't get more equations and less unknowns. The equations are all dependent. Okay, that is a very important point with Kirchhoff's law. Okay? So junction law says sigma II equals 0. Okay, so all the currents, arriving, the sum of currents arriving in a junction is 0. So in this case, I1 minus I2 plus I3 plus I4 minus I5 equals 0. Okay, that is Kirchhoff's current law. Now the loop law states that the voltage, the sum of the EMF in a loop is equal to the sum of is equal to the product of the current in the loop and the resistance present. So V minus IR, right? If you just sum all the EMS and you subtract all the when you go from negative to positive, you increase, right? When you move from negative to positive, you say plus, and when you go across a resistance and the current convention is this way, you say minus I times R, right? So when you go from the negative to the positive terminal of a battery, the potential increases. So the negative terminal is shown with a small line, positive terminal is shown with a big line. So you cross that, it becomes plus, right? So and then when you draw the voltage drop across the resistance is I times the value of that resistance. So when you go one whole loop, sigma Vi will equal 0. That is called the loop rule, right? So once in any closed loop, the sum of the voltage differences is 0. That is the loop law, right? So that pretty much gives you the loop law. So what I am now going to do is I am now going to introduce the a couple of quick examples, okay, and then next week I'll a little bit continue with this material because I don't think I can do justice to all the remaining material because there's a lot of material. Okay, so because this material definitely they always ask a couple of questions and then there's a lot of intricacies involved, notably when we go into Wheatstone bridge, etc. So those things I will look at in the next class. Okay, but let me quickly introduce the junction law one more time. Right, junction law states that the sum of the algebraic sum of all the currents entering the junction and leaving the junction is 0. The loop law states that the summation of EMFs in a loop is equal to the summation of the product of the current and the resistance in the loop. So add the EMFs, subtract the IRs, right, and you end up with 0. Okay, so that's sigma Vi equals 0, sigma II equals 0, the two basic laws. Okay, so now here's a really complicated junction. So how many equations can you get? So most often, right? So how many equations can you get? Typically, people pick all these junction points. So A, B, C, D, right? So using all these junction points, they say I1 plus, this is 4 amps, I1 plus 4 amps equals 3 minus 2. Okay, notice that here there is a negative current, but you stay with the convention. Okay, so on the left hand side, if you have all the incoming current, right? So, but the outgoing current, but it's minus, right? So incoming currents I1 plus 4A, right? Outgoing currents 3 minus 2A. Okay, so that gives you the result. Okay, so you can rewrite it also. Otherwise, all the incoming currents at A, right? All the incoming currents is I1 plus 4 minus 3 minus 2 equals 0. Okay, that's how he's done it. Okay, then he goes to B. So B also he does the same thing. 3 plus I2 plus I1 minus 2 equals 0. So from these two equations, he gets I1 and I2. Okay, so that's how he goes about it. Okay, now the voltage rule, right? What it says is, if you have an open voltage and you have an I coming in, the drop is equal to I times R. So you say that minus IR is when as you go around in that loop, right? Minus IR. Okay. If the current was said to be this way, then you say this way it is plus IR. Okay. So that's the important idea there. Okay. So now here is an example. Okay. He is going once around this loop, right? If you start here, start at a plus 8, this is plus and this is minus, so minus V1, right? This is another one, right? Minus V8, right? This is another one, minus 8. This is a plus 6 and a plus 10. Okay, so then goes once around this and he reaches A again. Okay, so when you go minus to plus, you say plus. When you go plus to minus, you say minus. Okay, so that's how he ends up with. Let me do it one more time. Plus 8 minus V1 minus 8 minus 8 plus 6 plus 10. Come back to the same point. Equals 0. Okay, so we come back to the same point. Equal 0. Okay. Just note the starting point. Go one full round, then you 0 equals 0. Okay, so that's how you do that. Okay, so now we need to find. So here he is giving you two equations, right? So if you said this is the equation. So how many unknowns, right? Typically, you make the currents the unknowns. Okay, so now the current here, if you say that is I1, then that will also be I1. Okay, now if this is I1 and this is I2, and this is I3 will equal I2 I1 minus I2. Okay, I3 will equal I1 minus I2. I2 plus I3 equals I1. Right? Therefore, I3 equals I1 minus I2. Okay. So now you have one unknown, two unknowns. Okay. So now you must write two loop equations. Okay. So you use the so this is one loop equation. This is another loop equation. Most people, they don't go for these big loop equations. They go for internal loop equations. This is one equation. This is one loop equation. So now let's write this loop equation. Plus 12 I3 times minus I3 times 2, right? Minus I1 times 2. Okay, plus 12 minus I1 times 2 minus I3 times 2. Minus I3 and I3 is I1 minus I2. So you end up with this equation. Now this loop minus 6 I2 times minus I2 times 2, right? And when you go this way, plus 2 times I3 equals 0. Okay, so using these two equations, you have two equations and you have two unknowns. Then you just solve for I1 and I2 using algebra, right? Two equations, two unknowns, you solve for equations, two unknowns using algebra. Okay, so that's how you solve these problems. But then that doesn't mean that you can you don't need to maybe reduce a needless loop using your existing knowledge about parallel circuits. Okay, so here you have one loop, two loops, three loops. If you solve it using one, two, three loops, you will still get the answer, right? But what he does do is he takes this 6 and 6 and then he says this 6 and 6 are in parallel, so I'm going to replace it with a 3. Okay, 6 and 6 in parallel is 6 times 6 divided by 12, which is 3, right? Which is 6 by 2, right? So he replaces it by 6 by 2, and tada, he's got just two loops. Then he solves for these two. If you just wanted this current and this current, you would just have two equations, two unknowns. Okay, so that's another clever way to solve these problems. My suggestion is that you spend significant amount of time, maybe a half hour to 45 minutes, going on the internet and then trying some problems. Otherwise, download our app, and now our app comes with also with the assessment module. You will love the assessment module, and you try it out with the assessment module, and you should be able to get a lot of value from that. Okay, so this question is a little trickier. Here he has a cube. Okay, now when you face a problem like this, right, you have to use also the symmetry in the equation. Okay, in a lot of these resistance problems, you must learn to use the symmetry in the problem. Okay, and we will do a little more with the symmetry when we also look at the Wheatstone bridge. Okay, but suffice it to say that if you had a connection like this, it is pretty clear that the current will break equally, right? So I1, I2, and I3 is a very symmetric problem, right? So I1, I2, I3, right? And so now when there is I1, I2, I3 going from here, right? So this is 3I, I1, I2, I3. Now this will break into two parts, and he's saying that is I by 2, I by 2. Then it reunites here at I, and I. Okay, so very, very interesting to notice that, right? So if you're not careful, you get it wrong. So these are not. That's why they are not that easy. Okay. So in this case, so you what is the effective currents, right? You can then evaluate that. Okay. So each resistance is R, right? So the current supplied by the battery is 3I equals 6V divided by 5R. Okay, so we will go over this in more detail next class because it's not so straightforward, right? So what is the equivalent resistance between points A and B? Is 5 by 6R if each of those resistances is R. Okay, so I will discuss that again next class. This is not so straightforward, and we've come to the end of this lecture. So next time I will continue with Kirchhoff's current and voltage law. I'll start with this example, then I will go to the follow-on example, and then we will go on to the next set of material which deals with the Wheatstone bridge and other related ideas. Then we'll do maybe a few problems relating to electricity, current electricity. Okay, so with that, I'm going to close today's lecture, and I want to once again remind all the students that about the offer that we have. Let me bring it up one more time. Okay, so the offer is valid until Independence Day. So it's an Independence Day promotion. You get 30% off, so it's $59.95 for a full year program. $59.95 is a very low price for a full year program. Please take advantage of it. Otherwise, you can get $39.95 for a 6-month program. And so that is what we offer. We have the same offer for Ramanujan, which is our JEE platform. So you go to play.google.com and then you can find it there. Okay, so let me quickly show you that in case you have not seen it. But this is our Independence Day program. I hope you can see it. 59.95. Okay, so now let me quickly show you where to go. Okay, one. Okay, so I'm going to show you where to go for. I hope you can see my screen, right? So this is where you go. You go to play.google.com and you say, you go to the search bar and you say Ramanujan, right? And when you go to Ramanujan, you see the JnanaMarga Technologies app. You click Ramanujan. Okay. Now, the other place where you can do it is just go to com.jnanamarga.ramanujan. Okay. Just go click com.jnanamarga.ramanujan. That will bring you straight to our app. Okay. So that will be the first thing you see. Go install onto your cell phone and you're up and away. Okay. Now, if you wanted Sushruta, just change it instead of Ramanujan. Just say Sushruta. Okay. And that will take you to Sushruta. You can then install Sushruta on your device and go about it. All right. So that's your, here you have the review. We have a lot of students who are taking advantage of our apps. And right now we have a promo for you. Please take advantage of our promo and go about downloading our app and using Ramanujan and Sushruta. With that, I'm going to end today's lecture and I will see you again next week. If it is Saturday, it's the class 11 material. If it is Sunday, we will continue with electricity and magnetism. And I will look to wind down current electricity. Then we will move on to Biot law, and we'll introduce electromagnetism, and then go on to Faraday's law, and then we will wind it down with a little bit of Maxwell's equations, and then move on to electromagnetic waves, and wrap up electromagnetic theory. Still a long ways to go with respect to electromagnetic theory. It is hard material, but these are the current electricity material requires practice. So we have a self-assessment module when you go to Ramanujan or Sushruta. Work with the self-assessment, use the self-assessment for now. We also have a test app on the way. Within a couple of weeks, you will start seeing the rollout of our test app just before the JEE exam is out, and so you can attempt a few of the test preps as well. And then in the meanwhile, we also have our mock tests, right? Mock tests for JEE and then mock tests for NEET. And you keep taking these tests and keep doing well. All right. So with that, I'm going to end today's lecture. I'll see you again next week. All right. So see you then. Thank you.